Here's the more extreme comparison. Namely, we suppose that we produce not 300 Higgs on that background, but 30,000 Higgs, so that's a factor of 100. Bumped up the Higgs cross-section or probability of being produced by a factor of 100, and then see what we get. And so that's just putting 30,000 in here for the Randon, and we just add that to the same old sloping we had before with 42,000 events. And then we get, here's the actual Higgs itself without any background. And this is these green ones here are the 2 GeV white Higgs, and the blue the half GeV Higgs, and both of them are pretty striking. They all have this characteristic, a bell-shaped curve, which is called the Gaussian distribution or normal distribution, which is how we generated them and how we'd expect them to look if this width was due to measurement error. And we will actually study this shape in a clearer fashion in a later lecture, because this type of experiment, the so-called normal distribution, is very important, because many things you will find are distributed normally. So here's the actual the result of this experiment, where we happen to make the Higgs 100 times more common. And here is the background. This I don't know what color it is, greenish color. Here we have the purple Higgs, and then the blue is the background plus the Higgs. So this is a huge signal. If you saw that, you would never have any doubts, and you'll be able to produce your results and your paper in a rather quick and straightforward fashion, which nobody would object to. The early resonance, the so-called resonance or particles people studied in particle physics were produced with signals like this, which are very clear. Recently, however, we're looking for much more subtle effects, and those subtle effects do not jump out like we see here, but rather require a lot of data and a subtle analysis to isolate. Finally, here's a lot of Python code. This was actually set as the homework for you to investigate. We have the same basis before. As I don't really want to worry you with accept reject methods, we do not have a sloping base. We just have a flat background. Here we have the Gaussian signal, and here we have the total, which is now just this flat background plus the Higgs. And then we have some plotting Python commands, which I didn't go through before. The figure Python command defines a new figure, and we gave that new figure a name, total wide Higgs bin 2 GeV. And then we did a histogram of it, which is this histogram command. We have 15 bins, and we run the histogram from 110 GeV to 140 GeV, and we set the opacity alpha to be 0.5 and the color to be green. So this is just a real basic Python plotting command. Here we have set the centers of the bins. And this is a little slightly subtle use of Python's automatic syntax for arrays. The 1 colon corresponds to taking the bin starting at not at the 0th but at the 1st. That's because we want the top edge of the bin. The -1 corresponds to running Python index from 0 to the upper index, which is 30 minus 1. And so this thing here, centers, actually gives you the center of each of the bins. It's an array of dimension 30 in this case here. And then we have here already the values is the number of counts in each bin. Then we set here the errors, which is, as I discussed, the square root of the number of events. We'll discuss that a little more later on. And here we have, we add some more stuff to our histogram. We plot not just the total. Here's the total, simple total. We call it simple total because it's not a non-sloping background. Here we plot the base, the background. Here we plot the Higgs, the Gauss, and here we plot the error bars. The error bars have a x value given by centers, a y value given by values, and they have error given by errors. And then we specify default line star, that's ls, marker, which is going to be an x, that's the midpoint of the error bars, and the color is black, and then the size of the marker we set to 6 points. So given that, we get this plot here, and you can see compare, we have these error bars here. I've shown you those on previous pictures. Here we actually give you the Python to produce it. You can see as by construction, the crosses, the markers at the error bars are always at the top of the bin value. That's by construction. And we have here the Higgs. Here we have the background, and the green is the signal plus the background. So that's the end for this this lesson, and we will continue our discussion the next time. Thank you very much.